Last time we followed a procedure for adding up the electric field of some macroscopic extended object, which was that we first divided the object into pieces whose electric field we knew. So the simplest thing is to divide it up into little pieces that we can approximate as point charges because we know the electric field of a point charge. Then we had to write an algebraic expression for the electric field of each piece. And that was actually the most challenging part because we needed an origin, an axis, and we needed to find an expression for delta Q, the amount of charge on each piece. And then we had to express all this in terms of some, it turns out to be an integration variable, whether you're doing an integral or not, the thing that varies with the location of the piece. So that was where all the work went. Then we had to add it up, which we might do using calculus or we might do numerically, and then we had to check the answer for reasonableness, and two checks we came up with are do the units come out right? And when we get very far away, does the object look like a point charge? And we applied this in detail to one thing, which was a uniformly charged rod of length L. And we actually managed to use calculus to get an expression for the electric field as a function of distance. And that's the thing we're usually interested in when we're doing this, as a function of distance, at a particularly symmetric location along the midline. So if the rod is, this is our rod of length L, the midline, but what we mean by the midline is the line a line that bisects the rod. And of course, there's actually an infinite number of these because there's one sticking out of the page and there's anything in the plane perpendicular to the rod, any lines that goes through the middle of the rod is a midline, right? And then we also looked at a special case. So special cases are useful. So in this case, this is a general expression for the field of the rod, but if we're close to the rod, then we get this expression that's a simplified expression, that's approximate expression that works pretty well, that's simpler, it gives us a simpler distance dependence. It looks like it goes like 1 over r. And then we kind of waved our hands at the derivation for a ring. We didn't do it in detail. If we have lots of time at the end of this discussion, maybe we will, but it's in the book and you can read it. And so for a uniformly charged ring and again at locations on the axis of the ring, so this is hard to draw in. It's kind of a 3D issue, but here's the axis of the ring, and of course the axis is equidistant from all parts of the rings, which is why it's symmetric. And so on that, for any location on the axis of the ring, we also got an expression for the magnitude of the electric field as a function of distance using the same. Okay. So what we're going to do today is we're going to look at some other shapes, but we're also going to try to apply the views and reason with these ideas, and we'll certainly be practicing with these in recitation. What you're doing in lab this week is you're actually going to do a numerical calculation of the electric field of a rod, especially at locations that aren't on the midline. Okay, so we have an expression for electric field that's somewhere on the midline like this, but what if it's here? You know, well, we don't know what that is. So we're going to be doing this numerically and exploring one of the basic ideas behind lab is to explore the goodness of the accuracy of your calculations as you model the rod by more and more point charges. So that's the basic goal of lab. Let's see. So let's try a question. So this is a simple question, and it just has to do with interpreting the meaning of the formula here. So we have this expression for the electric field of a rod, magnitude thereof. In this situation, what's the value of R? So here's what you said. Most people said 3, and 3 is indeed the correct answer in this case. So the message here is you don't have to memorize this equation. But do know what the symbols mean. So R is, of course, the distance from the rod. So if this is the rod, our observation location is here. That distance is R. And it's 0.04 instead of 0.4 because it was 4 centimeters. And we're calculating electric field in newtons per coulomb, which means we need to use meters. So if you said 4, you were in the right space, but you forgot to convert units. That is one of the most common problems you'll have on homework and quizzes and tests. If you said something else, then you have some work to do to make sure that you really understand what the meaning of these symbols is. Okay, let's try another question. So we have a rod with it's 50 centimeters long. It has a charge of 2 times 10 to the minus 8 coulombs. Lies on the x-axis. We have to calculate the electric field at a distance of 1 centimeter from the midpoint of the rod. Which equation should we use? Most people said 1, you should use the exact equation, although there were a number of. So we had 44% saying 1 and 33% saying 2, and some people saying 3. Now we can, this is, so here's what you said. Now, this is a matter that for some thought, but I think the question you have to ask yourselves is, what is the point of deriving these approximate expressions if we never use them? They're much easier to calculate, and they also give us information about distance dependence that we don't otherwise have. So when can we use an approximate equation? Now, actually, I think the most insightful answer here would be 3. You could use either the exact equation or the approximate equation, because there's rarely a situation in which you can't use the exact equation. But I think it's also legitimate to say approximate. So is 1 less than 50? How do you tell when R is a lot less than L? That's a good question. And there's some sort of taste and experience in there, but surely if it was 49 centimeters away, then 49 is not a lot less than 50, right? So if it's a millimeter away, so you need to use the exact. If it's a millimeter away, you can certainly get away with the approximate. I would say that for our purposes in general, we're mostly interested in something to a couple of significant figures at most. That 1 is a lot less than 50. And remember that the context here, so we've got this R squared plus L over 2 squared. So the real question is 1 squared much less than 25 squared. And so was 1 much less than, and so surely the answer is yes, right? So the approximate equation would be just fine here. However, it's not an unreasonable question. In fact, it's sort of the heart of the question. And one of the things that, if you have time, you can do in the lab is actually, although you'll mostly be calculating electric field of a rod at some location that's not on the midline, you are asked to actually do it on the midline. And one of the things you can do is actually just go farther and farther away and see what happens comparing it to an approximate expression. We do have some help from VPython here. So I'd like to show you 2 VPython programs that relate to this issue of where the equations we've derived are valid. Now, this particular program has to do not with how far away, but how close to the midline you have to be for this, to use this equation we've derived. Okay, so we derived an equation for the electric field on the midline, right? And so what this program allows me to do is to click at an observation location where I want to calculate the electric field. The electric field is calculated numerically, actually, and then displayed as an orange arrow. So if I click at a location on the midline here, then that's the orange arrow is the electric field at that location. Now, what's this green line? Well, so the red cylinder is the rod. The green line is just a line that's equidistant from the rod. That's always the same distance from the rod. So if I click at a location, if I want to know the field at a location that's the same distance from the rod but not on the midline, I can calculate it and compare it visually. So if I click way up here, I'm the same distance from the rod, but I'm not on the midline, and you can see that the direction of the electric field is really very different up here than it is along the midline. So using this equation is not all that useful. And if I click at a location that's not very far from the midline, the field is not actually very different from the field on the midline. So as long as we're sort of close to the midline, sort of close to the center of the rod, that's not an unreasonable approximation. Let's see how far we can go before it starts to really deviate. So, well, we're a little farther from the midline. It still looks about the same. A little farther. Now we're starting to see just a very slight change in angle, but not so much. Here, not awful. Now we're starting finally to see a little bit of deviation in the angle. But the really interesting thing is that we can actually go pretty far away, farther than one might think, from the midline, and have that equation that we derived for the midline actually be not unreasonable. Now notice that our equation does not give us a vector, okay? It just gives us a magnitude. And so if you need a vector, what you're going to have to do is look at the physical situation, draw axes, and figure out how to express your answer as a vector. In this case, the electric field looks like it's in the x direction using our standard coordinate system, and so you could just multiply by 1, 0, 0, and get the field. Whereas if you were on the other side, you would have to go the other way, right? Now, as terms of the distance from the midline, so here's a program that actually just calculates the magnitude of the electric field using the exact equation and the approximate equation, and then graphs them as a function of distance from the rod and compares them. So we're looking on the midline here, and what we're just doing is evaluating those two equations, the exact one and the approximate one, and this kind of speaks to Morgan's equation. The rod is a meter long, and so the x-axis is the distance from the rod, and the y-axis is the magnitude of the electric field. The red calculation the red line shows the exact calculation, the blue line shows the approximate calculation. So we get to 1/10 of a meter away, and they're still pretty much indistinguishable on this scale. We get to 20 centimeters away, and they're starting to differ, but not by a whole lot, really. And it's only when we start to get out here this is now half the length of the rod, so the rod's a meter long, we're 50 centimeters away. These answers differ, but certainly not by a factor of 2, right? By a fairly small percentage. So these approximate calculations are actually possibly more useful than you might really think. And the message here is that you shouldn't actually avoid them. Use them judiciously, but don't be afraid of using these approximate expressions. Okay. Let's go back to our discussion here. So one of the things that we would like to be able to do is to get the electric field of some things that are not rods and rings. Now, one of the things we can sometimes do is, and in particular, one of the things we're really interested in is the electric field of a plate, like a square or a round disc or a plate that's uniformly charged, because that just turns up a lot technologically and other reasons. So, so the next thing we want to do is look at the electric field of a disk. And so I'm going to try to draw this in a kind of a 3D way. So this is kind of, well, that's a pretty bad ellipse. So I'm drawing a circular disc, but we're looking at it kind of it's not in the plane of the page here. And of course, the symmetric axis, the symmetric line along which we might be able to get an analytical expression is going to be the axis of the disk, right? And so we could divide the disk into point charges and calculate the electric field of each charge and add it up. But in fact, we could also divide the disk into rings, because if we had, for example, if we divide the surface of the disk into, it shouldn't be pointy, into rings of charge, we know the electric field of a ring, so presumably we could just add up at some location on the axis the electric field of a series of concentric rings here. So we divide it into concentric rings, and we wouldn't have to go all the way to point charges. So let's just look briefly at a Python program that does this. So what we want is the electric field of a disk calculated by adding rings. So here's our disk. This is the axis of the ring, of the disk. And what we're going to do is divide the disk into concentric rings and calculate the electric field here at the origin. The disk is not at the origin. Okay. So here's the field of the first ring, and now we add the field of the second ring, and now we add the field of the third ring. And what we're doing is this incremental adding, this sort of keeping a running total, which is the way you usually add these things up computationally. Okay, so we've got this intermediate value, and then we add to it the field of the next ring, and the next ring, and the next ring, and the next ring. Now, the tricky thing about this here is, although we can just be using the equation for the electric field of a ring here on the axis, these rings don't have the same charge, because the larger rings obviously have more charge, but the radius is also different. So we actually have to not only take into account the bigger radius, but we have to figure out how much charge there actually is on this ring. So that's the sort of geometric challenge computationally, and so we keep adding, and we add concentric rings until we get to the rim, and then we've got the total electric field on the axis, which, not surprisingly, for a positively charged disk, points away from the positively charged disk. Okay, so again, we have the question, what if we're not on the axis? And so here's a disk that's actually approximated by point charges so that we can get the electric field at locations not on the axis. And so what we're going to do is just use our procedure and pick a whole bunch of observation locations that run just along a line through the disk, because we'll get sample near the center and near the edges that way. And so we're just going to add up the field of all these point charges. And so here's what we're doing it for different observation locations. Okay, and we see that if we look at it edge on, the electric field, of course, on the axis points directly away. If we're pretty close to the center, that's not actually a bad approximation, but as we get out toward the edges, the field's in a very different direction and has a different magnitude. And so we would actually need to do something other than use the equation that's valid for the midline. Right? So let's see what we can do with this algebraically. And you've got, I think, the basic idea. So I'm not going to grind through lots and lots of algebra and calculus here, but let's just kind of think about what we're going to be doing here, and I'm going to try to redraw this in such a way that it's just a little cleaner so we can see what we're doing. So here's our disk, and what we're going to take is a ring here, kind of in the middle of the disk. The radius of the disk is capital R, and the radius of this little ring that we're going to take is, we're going to call it small r. And so the width of the ring is going to be a delta r. And because of cylindrical symmetry, we're going to call this the z-axis, so that we can get the electric field at some location on that axis. So we do exactly the same procedure. We divide it up. So we divide it up into these pieces, which are rings, and we're going to take this representative ring, which is some radius r, little r. And so the contribution of one piece, we're going to call that delta E on the z-axis, is going to be just the equation for the field of a ring. So 1 over 4 pi epsilon 0 delta Q, the charge on this ring. So this is a delta Q times z, our distance. So here's our z, distance from the disk, divided by r squared plus z squared to the 3/2. And so what's delta Q? Well, we can think of delta Q, the amount of charge on the ring, is the charge over the whole area, the charge per meter squared on the ring, for the whole ring, times the area of the surface area of this little ring. So we're going to call that delta A, area of the ring. And so that's going to be a Q over pi times capital R squared, so charge per area of the ring. And so what's the area of the ring? Well, if you think about this ring, it's kind of like a long rectangle rolled so its edges meet. So if you actually unroll the ring, then the distance along one edge is 2 pi times little r, the circumference of the ring, and the distance along this edge is delta r. So the area, so here we're going to be multiplying by 2 pi times little r over times delta, sorry. 2 pi little r delta r, which is the area of the ring. And so we can go to the limit. So now we can write dE sub z is, if we do some algebra canceling things, we've got some pi's and whatnot that show up here. And so we end up with a 1 over 2 epsilon 0 Q over a pi r capital R squared, so those are all constants, times Z over R squared plus Z squared to the 3/2 dr. So our delta R turned into a dr, and our delta Q turned into this dq thing here. And so E sub Z is just going to be the integral of this expression here. And the integration limits are, well, what's varying here? What's varying here is the radius of the little ring we're adding in. So it would start at 0 and go to R. And what we end up with, and this is in the book, so I'm not actually gonna crank through it here, is an expression for the magnitude. Again, this is the magnitude of the field on the axis. Is we usually write it this way. We could write a Q over pi r squared, but what we're really going to do here is write it as the charge over the area, the charge per unit area of the disk. Because if this disk is big enough, it actually doesn't really matter very much whether it's round or square. We're going to get the same field over 2 epsilon 0 times the quantity 1 minus Z, our distance from the ring, over capital R, the radius, the distance from the disk, capital R squared plus Z squared to the 1/2. Now, it's a little hard to tell how that falls off with distance. So this is valid at any distance. So but we'd like to see if we can get a cleaner distance dependence. So what if we're close to the disk? Then Z is less than R. And so E sub Z would be approximately, we have this charge per unit area over 2 epsilon 0 times 1 minus, well, if Z is a lot less than R, then Z squared is going to be a lot less than, even more smaller than R squared. So we can say that Z squared in this expression here is approximately 0 compared to R squared. So we get a 1 minus Z over R. But that leads us to say, well, what if we're really close to the disk? So we have Z is much, much smaller than R. Then E sub Z would actually be Q over A over 2 epsilon 0. That quantity is nearly 0. So in fact, we'd end up with this expression for the electric field. So if we're really, really close to the disk, then in fact, the electric field of the disk is actually independent of distance. It's nearly constant. So we've actually learned to make a way to make a electric field that doesn't vary very much with distance. And so if we're very, very close to a charged disk or a charged rectangular plate, so if we're somewhere in this region here, the electric field is essentially uniform and constant. And that's kind of an interesting distance dependence. So this is the really exact equation here for any value of z. This equation is sort of an intermediate thing, and this is if you're really, really, really close to that. Or the disk is really, 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 really big. So there's a situation that's so common in technology that, and has a special name. If we have two disks with equal and opposite charges, this is actually called a capacitor. And we'll talk in future chapters about how they're constructed and how you might get charge on one. But so let's say we've got two really, really, really big disks. I'm going to draw them of finite thickness here. And I'm going to draw kind of a squiggly line here, indicating that I'm only drawing the middle section. So this goes on. It's very big. So our radius of the disk is very large. And so here's our other disk. So we're looking at the reason I'm making this point is that it looks here like the gap between the disks is large compared to the radius of the disks, and I'm trying to indicate that that's not true. So the gap is much, much smaller than R. Okay, so this is R. And let's say that these are metal, so they're conductors, and we've charged them by induction, say, or something like that. So that this one has a fairly large positive charge, and this one has a fairly large equal and opposite negative charge, and they're polarizing each other so that the charges are mostly attracted to the center, but there are actually a few charges on the outside, not so many. And by convention, we typically call this gap distance S here, so this distance for separation. So S is much less than R here. So what is the field at a location inside here going to look like? Well, we're going to have two contributions to the field, right? So at some location here, the electric field due to the positive plate is going to point away from the positive plate. The electric field due to the negative plate is going to point toward the negative plate. And so our net electric field at this location is going to be away from the positive plate and toward the negative plate. And so, at locations inside this capacitor here, so inside, the electric field due to the negative plate has the approximate magnitude Q over A times 1 minus Z over R. We need an origin somewhere, so we'll put the origin That's the negative plate, so it looks like we're putting the origin here at the negative plate. Okay, so here's our origin. X equals 0, so Z equals 0. And the electric field due to the positive plate is Q over A times 1 minus S minus Z over R. And so if we add them up, though, it turns out that we actually get an electric field E net, which is actually, there's a Q over A over epsilon, over 2 epsilon 0. These terms Z over R and S minus Z over R are really actually fairly small. And so we're actually gonna end up with an electric field inside the capacitor that's constant, it's uniform, it's the same, same here, for example, and here, and it's nearly uniform. Now this works out sort of amazingly well, actually. And so if we look at this in Python, what we find is that so what is this? This is a calculation of using those equations. So Q over A times 1 minus Z over R and Q over A times 1 minus S minus Z over R. So the red, down here, the red line is the electric field of the positive disk as a function of distance from the positive disk. I guess the origin is the positive disk here. The blue line is the electric field of the negative disk as a function of distance from the negative disk. And the magenta line is the sum up here. It's the sum of those two things. And you can see that although the fields of the individual plates, there's the red line and the blue line down here, vary kind of infinitesimally, but not very much with distance, the sum is actually really, really, really constant. So in fact, it really works out that inside these two charged plates, as long as you're not right at the edge of the plates, you've got this super uniform electric field. Okay, so Hunter, I'm not sure I quite understand your question. Are we talking about the electric field at a different location? Yeah, okay, so that's what I actually want to do. So, so we looked at the electric field in between the two plates. But let's see if we can think about the electric field outside the plates. What's that going to be like? Oops. Oh, I see what you're saying. You're absolutely right. I drew it wrong. Should have been minus here. Thank you. However, it does raise the question of what the electric field would be. Let's fix it here, shall we? Okay. What would the electric field be? So we know inside it's very uniform. What would it be at some location out here? Well, what we're going to get is that a location outside here, the electric field in the z direction is going to be something like, it's the sum of the two the fields of the two plates, right? So we're still using superposition. So we've got a 1 minus z over r plus a 1 minus s minus z over r here. And so what we end up with is a, oh wait, let's be careful here. This is a 1 minus z over r, and this is a minus this quantity, and that's a z plus s over r because so here's z, so and so they don't quite cancel. We have, qualitatively, we can see that the electric field due to the positive plate is going to go that way. The electric field due to the negative plate is going to go that way. And so we're going to get an E net that's small, but not zero. And this should look really familiar because it's just like the dipole, right, on the axis. And so what we're going to get outside here is something that looks kind of like Q over A over 2 epsilon 0 times the ratio of the gap between the plates to the radius. And so as the plates get bigger or the gap gets smaller, this field outside approaches zero. Okay, it gets very, very, very small. So so it can be small. There's a name for the field outside, a technical name. This is called the fringe field. Is the field outside the capacitor here. And of course, over here, we're going to end up with a small net field here, whereas the field in here is going to be really big inside. So again, we have these. Now we have two more equations. So we had the field of a rod, we had the field of a ring. Now we've got the field of the disk. So we had these three expressions, really. Q over A over 2 epsilon 0 times 1 minus Z over R squared plus Z squared to the 1/2 for any value of Z. Q over A over 2 epsilon 0 times 1 minus Z over R for Z small. Q over A over 2 epsilon 0 for Z very small. And then E of a capacitor, these two charged plates, equally and oppositely charged plates. Inside, it's just Q over A over epsilon 0. And outside, it's Q over A over 2 epsilon 0 S over R. Again, we're not going to memorize any of these. So would the field of a disk be generally applicable to any flat shape in a general sense? Yes, that's exactly how we're going to treat it. So So for example, if we say that we have a big, a charged rectangle, of width W and height H, then the electric field of this charged rectangle on some axis perpendicular to the rectangle, near the center of the rectangle, would just be E of the plate. We would use our equation for the disk, so we'd say it was Q over A over 2 epsilon 0, but now A is width times height. It's not pi r squared, right? So that's the basic idea. So let's work a problem. So here's an example. The critical, what's called the critical electric field, the critical field in air, is where air breaks down, ionizes, and becomes a conductor. Is approximately 3 times 10 to the 6th newtons per coulomb. And so let's say if we had a capacitor of radius 50 centimeters and the gap between them of 1 millimeter. So the radius is half a meter, but the gap between the plates is only a millimeter. What's the maximum charge we can, and there's air in between them. So what's the maximum charge you can put on the capacitor before the air between the two plates ionizes and you get a spark conducting charge from one side of the one plate to the other? Okay. So we're concerned with the electric field inside. And this is a good capacitor. 1 millimeter is a lot less than 50 centimeters. So this is much less than R. So we're justified in using the approximate equation here. So we're going to say, we'll look for the field at which the amount of charge at which the field inside reaches the critical field. So E in the capacitor is 3 times 10 to the 6 newtons per coulomb, which is equal to the charge per unit area over epsilon 0 inside the capacitor. And so we're gonna, what are we solving for here? We're definitely solving for Q, the amount of charge that produces this field. So Q is going to be equal to 3 times 10 to the 6 newtons per coulomb, that's the critical field, times epsilon 0 times the area of the capacitor, yes. So that's going to be 3 times 10 to the 6 newtons per coulomb. What's epsilon 0? well, it's 1/4 pi epsilon 0 times 4 pi. Its value happens to be 8.85 times 10 to the negative 12th coulomb squared per Newton meter squared. And now the area of the capacitor, what does the area mean? Well, it means the surface area of one of these plates. So that's pi times 0.5 meters squared, right? So B Python to the rescue. So we'll just call it maximum charge. So epsilon 0 is 8.85 times 10 to the negative 12. The radius is 0.5 meters. The electric field is 3 times 10 to the 6 newtons per coulomb. And so the area is pi times r squared. So Q, where do we decide Q is going to be? Q is going to be E times epsilon 0 times the area. And so it looks like we can only get about 10 to the negative fifth coulombs, 2 times 10 to the negative fifth coulombs on this. So there's one other thing we can do with rings. We can actually get the E of a uniform sphere. And I'm going to say spherical shell. This means it's hollow. I mean, there's just a layer of charge, like there was a layer of charge on the outside of the ball, but no charge inside. So just a shell of charge. And this is, you can do it with calculus. It's actually at the end of this chapter. It's one of the start sections. So if you'd like to look at it, you can see how to do it. It's just kind of long. Are there practical applications? Yes, there absolutely are practical applications of these things. In fact, the electric field of 2 plates is actually really important. It's one of the ways that you accelerate particles, like in old-fashioned television sets. The CRT kind, what you had was 2 plates that had a uniform field, and actually electrons were accelerated through these plates and then steered by magnetic fields so that they hit a fluorescent screen, which actually, so there's, and so there are lots of technical applications. We'll be working with capacitors and circuits, actually. But I want to show you how we can get the electric field of a uniform sphere. Let's see, there we go. In Python, because we told you in we just kind of told you in chapter 13 that the field of a uniformly charged sphere looked like a point charge outside with 0 inside, but now we can actually see how this works. So here's our sphere. We'll assume it's uniformly charged on the outside, and we're gonna look at a location outside the sphere. Okay, so our observation location is here. What are we seeing here? The orange arrow, which is very small at this point, is the net electric field. And the green arrow is the electric field just contributed by this ring. And it's plotted, it's really measured at the same location, but it's plotted displaced just so you can see it. And here's the first ring. That's just that little teeny ring there. And so what we're going to do is just cover the sphere with rings. And you can see that we're not doing a great calculation because the rings are actually pretty far apart. And we get a much better answer if we were. So far, all the rings are contributing in the same direction, but the fields are getting smaller because the rings are getting farther away. And we finally get to the end, and we've got this net electric field that that points away from the sphere. And we do need calculus to show that this is exactly the same as the electric field would be if we took all these rings, Superman took all these rings, squashed them down to a point, and left it at the center of the sphere. Okay, so that's not terribly exciting, but it's basically how the calculus works. A more interesting thing is to look at what happens inside the sphere. So an observation location inside the sphere. And it turns out that this works for any location inside the sphere, which is very interesting. So here again, the orange arrow is our net electric field at this location, and the green arrow is just the contribution of this ring displaced so you can see it. So we want to get is the net, and so we got a sphere that has uniform positive charge all at the outside. It's like a ping pong ball. It's a hollow sphere, and we're going to look inside and see what the field is. So we start adding rings of charge, and the field's getting bigger and bigger, although the contributions are getting smaller because the rings have a bigger radius, so the charge is a little farther away now. Okay, and I'm going to have to zoom out a little bit because the electric field is getting really big. But then something interesting happens. As we get rings that are really near the observation location, the contribution of each ring goes almost to 0, and if there's a ring right there, it's actually going to go to 0. And now we can see if we look here that the field due to the individual contributions of the rings are starting to go the other way because now the rings are on the other side of the observation location. And so we keep adding up those rings, and then we see the net field actually decreasing because we have all these contributions from these rings that are on the left of the observation location. We've drawn it here. And when we add up, get to the very end, and we add up all the rings, we can see that in fact the net field is essentially 0 here. That orange arrow is just kind of a flat square showing where the tail of the arrow would be. Now that's actually pretty interesting because we didn't do a very good job of using lots of rings. Okay, the rings are really widely spaced just so we could see the arrows. But the result, what we see here qualitatively, and I'll run it again just so we can see it, is that even though the rings of charge that are closest to the observation location make an electric field pointing to the left, there are an awful lot of rings of charge that make small contributions to the right, and it adds up to 0 at any location inside the sphere. And that's actually pretty counterintuitive. Now, if there's something else outside the sphere making a field, like you stuck a proton up here in the left corner, then that would contribute to the net field inside the sphere. But from the charge on the sphere, the contribution ends up being actually 0. So what we have is a billiard ball, say. So it's a solid ball, but there's negative charge uniformly spread over the surface of the ball. Now, this is a uniform shell of charge because the inside of the ball is not charged, it's neutral, right? I mean, so we just have this shell of charge just kind of on the outside. Okay, given what we just saw about electric fields here, and really do think about what we just saw about electric fields here. Which of these diagrams best shows the polarization of molecules inside the ball due to the charge on the surface of the ball? And what this shows is that 15 people paid a lot of attention and drew the correct conclusion, and 61%, 23 people let themselves be fooled by reacting and not thinking about electric field. So the answer is indeed 3. So if we take seriously what we just saw, then we have to conclude that at any location inside this ball, the net electric field is 0 due to all the charges on the surface of the ball. And therefore, there is no polarization. You have to take this seriously. Why is 1 not the right answer? Well, yeah, so let's consider this molecule here, okay? There is a negative charge right next to it. And that's very close, so it has a big effect. But there's all these negative charges here. Let me draw it this way. All these negative charges here far away that would polarize it in the other direction. And so, in fact, these all, if you take superposition seriously, the effect of these completely counteracts the effect of those, and you do not get any polarization. So, bravo, those of you who actually thought about field and weren't confused. Okay, this is the end of our discussion of electric field and distributed charges. We will practice some problems in a recitation this afternoon. Okay, so in chat, what's the most important conceptual idea in terms of getting the electric field of charges distributed over solid surfaces? Okay, some of you are saying things that are kind of right, but you're confusing the words charge and field. And at this point, that's kind of disturbing. So charge and field are 2 different things. And you need to distinguish between them. Okay, so a lot of these things you really need to rethink what you're saying here because they don't make physical sense.